In this podcast, we will be looking at solving systems of three equations with three unknowns. Now, before we do that, we need to talk about what a solution to a system of three equations with three unknown is. A solution is an ordered triple, which causes all three equations to be true. So as an example of that, I give the problem is the triple 4, 1, 2 a solution of the system that is shown here. Now, to see whether it is, we have to plug the 4 in for x, the 1 in for y, the 2 in for z, and see if all three equations are true. So let's start. Plugging the 4 in for x, I get 4. Plugging the 1 in for y, I get minus 2 equals 2. Well, that one's certainly true. Again, plugging the 4 in for x, I get 8. Plugging the 1 in for y, I get plus 3 equals 11. Well, that's certainly true. And plugging the 1 in for y, I get 1. And plugging the 2 in for z, I get minus 8 equals negative 7. That's true. So this triple 4, 1, 2 would be a solution to this system, not because it solved one equation, but because it solved all three. Now, how do you go about coming up with the solution? How do you solve a system of three equations? And to do that, let's recall how we solve a system of two equations. I've got two equations with two unknowns over here on the side. I've made it kind of simple to save time. The way we solve a system is we appropriately adjust the equations, then we add them up to remove a variable. So here, if I just straight add them, I get 3x equals 9. I divide both sides by 3, and I get x is equal to 3. Now, once I get that x is equal to 3, I back substitute. Like I could go to the second equation and get 3 minus y equals 3. And so y would have to be 0. So my solution is x equals 3, y equals 0, an ordered pair solving a 2 by 2 system. So the key to solving a 2 by 2 is to reduce it to a 1 by 1 and solve the 1 by 1. Well, similarly, the key to solving a 3 by 3 is to reduce it to a 2 by 2. So let's take a look at these three 3 by 3 systems and see how we would reduce them to 2 by 2s. In the first system of our first example problem, you don't have to reduce it to a 2 by 2. If you just pick off the first two equations, that is a system of two equations with two unknowns. So you solve those for x and y. You take your value you got for y and plug it into the third, and that gives you z, and you've got your solution. Now, if we go to our second system down here, it does not give us a system of two equations with two unknowns. However, it does give us one equation with two unknowns, so that's a good starting point. Now, the two unknowns are x and z. So if I could come up with one more equation that only had the two unknowns x and z, I would have the solution to my system. Well, that's not too hard to do. Multiply the last equation by 2. And you get 4x minus 2y minus 6z equals 6. Add that to the second equation. X plus 2y minus z equals 1. And you get that the y's zero each other out, so 4x minus 7z equals 7. And there's your system. Your first equation in two variables, x plus z equals 3. Your second equation in two variables, x minus 7z is equal to 7. You solve that, and then you use those two values to solve for your y. Let's go on to the third system. In the third system, we don't have any equations in two variables, so we've got to generate both of them. Well, let's see. Is there an easiest way to do that? Now, let me make it clear. You can pick any variable that you want to solve for, and you can solve the equations for that variable, or you can eliminate that variable twice, and that will give you a system of two equations and two unknowns. But often there's a best way or an easiest way to do it. And it looks to me like with this system, the easiest variable to eliminate twice would be y. For example, I can eliminate y from the first two equations by just adding them up just as they are. X plus 3x would give me 4x. Negative y plus positive y would give me 0. Plus 3z minus 2z would be plus z. 8 plus negative 2 would be 6. And there's one equation with two unknowns, and the two unknowns are x and z. Now if I can eliminate y one more time, I'll get my second equation in x and z. Well, let's try the first equation with the third. To do that, I'll multiply the first equation by 4. So I'll get 4x minus 4y plus 12z is equal to 32. And when I add those up, I get 6x plus 13z equals 32, and there is my second equation in x and z. And now I solve for x, solve for z, plug it back in probably to equation 2 to get my y, and then I have my x, y, and z. So that is how you reduce a system of 3 equations and 3 unknowns to a system of 2 equations and 2 unknowns. Then the 2 equations and 2 unknowns go down to 1 and 1, and then you back substitute for your answer. Well, where do these 3 by 3 systems come from? Well, like all algebraic equations, they come from word problems. So let's see a word problem that sets up in a 3 by 3 system. It says a certain brand of razor blades is sold in packs of 6, 12, and 24 blades, which cost $2, $3, and $4 respectively. So what we're saying here is a pack of 6 blades is $2, a pack of 12 blades is $3, etc. If the store sold 12 packs containing a total of 162 blades and made $35, how many packs of each type were sold? If we're going to solve this algebraically, we need to define some variables. How many packs of each type? There were 3 types, a 6-pack, a 12-pack, and a 24-pack. So we're going to need 3 variables, one for each type of blade. So I'm going to say let x be the number of 6-blade packs sold. And you can see what y and z are going to be immediately. Y is going to be the number of 12-blade packs sold, and z is going to be the number of 24-blade packs sold. And now we've got a variable for the number of each type of pack. Now we go to our clues. It said the store sold 12 packs. That's our first clue. So if I take the number of 6-blade packs sold, and I add it to the number of 12-blade packs sold, and I add that to the number of 24-blade packs sold, then I get the total number of packs sold. And there's my first equation. Now the second equation deals with numbers of blades. Suppose I sell one 6-pack, then I would be selling 1 times 6, or 6 blades. Suppose I'd sold 2 6-packs, then I would be selling 2 times 6, or 12 blades. Suppose I sold x 6-packs, then I would be selling x times 6, or 6x blades. So the number of blades sold in 6-packs was 6x. The number of blades sold in 12 packs was 12y, and the number of blades sold in 24 packs was 24z, and that has to equal the total number of blades sold, which was 162. My last equation is based on money. It says that the store made $35. Well, if I sold one 6-pack, I'd get 2 times 1, or $2. If I sold 2 6-packs, I'd get 2 times 2, or $4. If I sold 3 6-packs, I'd get 3 times 2, or $6. And if I sold x 6-packs, I'd get x times 2, or $2x. So the number of dollars sold selling 6-packs plus the number of dollars made selling 12 packs plus the number of dollars made selling 24 packs is equal to the total number of dollars made, and that gives me my system of 3 equations and 3 unknowns, which we now would solve to get the solution to the problem. And that completes the podcast on systems of 3 equations with 3 unknowns.